Assalamualaikum warahmatullahi wabarakatuh and hi. We are from Group 19 here presenting our integrated project entitled The Production of Phenol.
Introduction. Phenol is an aromatic compound consists of benzene and hydroxy group. This chemical present in colorless to white color in form solid and liquid and have distinct odor. Phenol also proven to be effective antibacterial, antifungal and antiviral agent. In hospital, phenol is commonly found in disinfectant used to sterilize medical equipment. Phenol also can act as antiseptic, which is substance that will kill microorganisms on living tissue. Phenol can use for the production of phenolic resin with formaldehyde and BPA. This table shows physical and chemical properties of our raw material and product, which are cumin, oxygen, phenol, and acetone. And this data we use for our calculation.
We move on to the next slide, which is demand and supply of phenol. The demand of the global phenol market in 2019 was around 13.4 million tons, and it is expected to reach approximately 60 million tons by 2025, with an expected CAGR of around 3.4% during the forecast period. The global phenol market is expected to exhibit the CAGR of around 5.5% between year 2020 to 2025. The supply of phenol is around 90 million tons by 2019 and anticipated to reach 12.4 million tons from 2019 to 2025. As you can see at the right side is a graph of demand and supply for phenol. The graph shows an increasing pattern of demand and supply for each year. The companies producing phenol is growing rapidly in various countries, so this is some list of companies producing phenol. The next part is future market potential. The phenol market was valued at RM 90.85 billion in 2019 and is projected to reach RM 125.12 billion by 2025 at a CAGR of around 5.5% from 2020 to 2025. The growth of sterilization industry and increasing demand of effective disinfectant due to this pandemic COVID-19 are the major drivers that have contributed to the growth of the market. Thus, phenol price is significantly increased by the last 5 years and will grow rapidly towards 2025. Figure 2.3 global phenol market shows the historical market and forecast from 2015 to 2025. You can see the change in trend for the global phenol market. Planned capacity of production of phenol. Based on the global demand and supply, by the year 2025, the production rate of the plant is estimated as below. The demand value is 60,380,000 tons per year. For the supply value is 12,410,000 tons per year. Next, we need to find the division by minus the demand value with the supply value. So we got 3,970,000 tons per year and convert it into kg per year, we got 3,970,000,000 kg per year. Next is the production time a day, 24 hours, and for the maintenance is 416 hours per year. So we find the production time a year, 365 days time with 24 hours minus with 560 hours, we got 8,184 hours per year. Finally, we can find the plant capacity, which is 48,509 kg per hour, approximately with 48,500 kg per hour, and we convert it into tons per year, we got 568,000 tons per year.
For the production of phenol, the process chosen is through oxidation of cumin that occurs in a packed bed reactor. In the reactor, the reaction that occurs at 85 degrees Celsius and 7 bar will lead to an intermediate product, cumin hydroperoxide, and an unwanted byproduct, dimethyl alcohol. With copper oxide nanoparticle as catalyst, the reaction will occur with 80% cumin conversion and 75% cumin hydroperoxide selectivity. Next, the product from the packed bed reactor will be fed into a flash drum to remove oxygen and nitrogen gas from the system. The remaining liquid product is then fed into a distillation column where dimethyl alcohol is removed through the bottom. The product in the distillate, which is cumin hydroperoxide and unreacted cumin, is then fed into a continuous third tank reactor where cumin hydroperoxide is decomposed to produce acetone and phenol with sulfuric acid as catalyst. The reaction occurs at mild condition, which is 70 degrees Celsius and 5.5 bar with 90% cumin hydroperoxide conversion. Next, the product from the CSTR is fed into a distillation column in which acetone will be removed through the distillate as a byproduct. The bottom product is then fed into a distillation column for phenol purification, where phenol is released to the bottom with 99.7% purity. For the packed bed reactor, the mass balance is calculated with 80% cumin conversion and 75% cumin hydroperoxide selectivity. For the input stream table and output stream table is shown here, in which the flow rates calculated for input and output stream is balanced. For the energy balance in the packed bed reactor, the heat calculated is negative 1.6 exponent 16 kJ per hour, which the negative sign indicates that the process occurs is an exothermic reaction. Next, the mass and energy balance for the continuous third tank reactor is calculated and shown here. For the mass balance, the flow rates calculated for input and output stream is shown, and it is balanced with 48,500 kJ per hour of phenol produced. For the energy balance, the heat calculated is negative 3.3 exponent 14 kJ per hour, which is an exothermic reaction. For the overall mass balance, the input stream and the output stream flow rates is calculated, and however, the values calculated is likely not balanced.
And here are the overall mass balance for the whole plant, which the inlet streams are stream 1, stream 4, and the outlet streams including stream 13, stream 18, 26, 30 and 32. For the environmental and safety issues, the yellow stream and in the figure shows the outlet stream that contains waste generated for the whole plant, and the table shows the quantity of the waste for each component, such as oxygen gas, nitrogen gas, cumin hydroperoxide, and dimethyl alcohol. For the waste gas, nitrogen can be separated from oxygen by using membrane separation. The oxygen gas can be released to the air as it does not contain any hazardous effect. Cumin is a waste chemical stream constituent. Incineration may be improved by mixing with a flammable liquid. For this CHP, method for the treatment of the cumin hydroperoxide is incineration. And the last one, dimethyl alcohol. The best method is by offering surplus and non-recyclable solution to a licensed disposable company.
The production of phenol from cumin is a liquid-based oxidation process, and it is catalytic process. Catalytic processes are often carried out in packed bed reactor. which is also known as a feedback reactor. Feedback reactor is used in this process. The reason why we are using this reactor because of the plug flow behavior, lower maintenance cost, improve contact between two phases in a chemical process. The next reactor we are using in our project is continuous stir tank reactor. CSTR is better for indefinitely long production run of one product or set of product. The most widely used catalysts in the production of phenol include copper oxide nanoparticle (CuO) and sulfuric acid. Copper oxide nanoparticle (CuO) is excellent catalyst not only regard to the reaction activity but also with regard to the CHP selectivity. For the next one is sulfuric acid. We are using as a catalyst in decomposition of CHP. The reason why is because of the high conversion in producing phenol from CHP is obtained. The next one is a process selection. We are using Sumin to phenol process. This process produces high purity phenol and acetone by Sumin oxidation route. Advanced CHP cleavage for high product selectivity. And the raw material needed for our production of phenol is Sumin and oxygen. Sumin will undergo oxidation process. As a result, CHP and DMBA will produce. Based on the general mole balance equation, flow rate of A in minus with the flow rate of A out plus with degeneration, which is integration of RA respect to V equal to accumulation. We assume that the condition is steady state, so dNA over dt is equal to 0. Then we assume that the condition is well mixed, therefore RA is the same throughout the reactor. Then we will obtain the equation below. Then rearrange the generation and write down in terms of conversion. Finally, we will find the mole balance of CSTR equation. Next is the kinetic rate expression. So the equation shows the decomposition of CHP to produce phenol and acetone. From the equation above, we can find the reaction stoichiometry and also the rate law, which is negative RA equal to KCA. By taking Sumin hydroperoxide as the basis, we can perform the calculation and substitute into the rate law equation, and finally we will find the kinetic rate expression, which is KCAO in bracket 1 minus X.
For the separation process, the separation unit chosen is distillation column S3 for acetone removal. Distillation column is chosen due to the fact that acetone is a valuable byproduct and we wanted to maintain a high purity of acetone, and this can be done using distillation column. The temperature for the distillation unit is selected with taking boiling point of the component into consideration. Acetone, the most valuable component, is selected as the light key component and cumin is selected as the heavy key component. In the distillate stream, acetone is removed with 96% recovery and cumin is removed through the bottom with 82% recovery. Next, the table shown here is the flow rates and composition calculated from the mass balance. The mass balance value is compared with a SuperPro simulation software, and as you can see here, the error calculated value is very small, hence we can tell that the calculation is accurate. The heat duty for the column, reboiler and condenser is also calculated and shown here. Since there is 4 components involved in this distillation unit, hence we use shortcut method to design this distillation unit in which the minimum number of stages is calculated using Fensky equation and the calculated value obtained is 2 stages. For the reflux ratio, we use Underwood equation with Q equals to 0.60 and reflux ratio obtained is 0.6664. For the number of theoretical stages, we calculated using the Gilliland correlation, and the calculation is summarized into a table, and the value of theoretical stages obtained is 4 stages with trade efficiency of 50%. For the fifth stage location, we calculated using the Kirkbride empirical equation, and the number of stripping section is 3 stages and the rectifying section is 1 stages. Feed enter the distillation column at stage 1. Lastly, the diameter and height of the distillation column unit is calculated, and the column diameter calculation is summarized in a table form, and the value of diameter obtained is 0.385 meter, which is also equivalent to 0.4 meter. For the column height, the height of tray is calculated by multiplying the tray spacing and number of stages, and the value obtained is 1.22 meter, and the total height of the column is the height of tray plus an additional height which is for the condenser and reboiler, and the value obtained is equivalent to 3 meter.
For the computer-aided plant design chapter, SuperPro Designer and Symmetry Simulation is used to testify and validate the material balance for the production of phenols. Here, the simulation report of the continuous third tank reactor R2 by SuperPro and Symmetry. So here we can see almost of the percentage error is 0. So it is valid. So here, another example of the comparison between manual calculation, SuperPro and Symmetry simulation. So we can see here the simulation report of packback reactor R2 by SuperPro and Symmetry, and also the percentage error for all the component is 0.
Chemical Engineering Computation 2. This chapter have 2 parts. Part A, we need to develop a program of mass and energy balance for distillation column. This program allows user to enter any data to run the program. For mass balance, user allowed to put only positive value. If user input negative value, the program will display notification for user to input a new positive value. The total inlet and total outlet from the program will get balanced. The error between manual calculation and MATLAB we get is 0.0008%. For energy balance in MATLAB, heat release we get is exothermic reaction, same as manual calculation. The error percentage between manual calculation and MATLAB is 0.0216%. Numerical method is used to validate the one parameter from the part A. The method we use is Newton-Cotes formula, which is trapezoidal rule, and the parameter we use is inlet enthalpy of cumin of distillation column. This is the equation we use. From the program, I indicate the inlet enthalpy of cumin, and the value we get from the program is 12340.327 kJ per kilomole. So, we calculate the error between the manual calculation and the coding we develop. The error is 0.206, and for the error of trapezoidal rule we get is 0. Since the error is 0, the parameter is valid. As conclusion, phenol is an aromatic compound used in hospital as phenol-based disinfectant. Phenol is synthesized from decomposition of cumin hydroperoxide and produce side product, which is acetone. Waste product for our production is cumin hydroperoxide of gas, and dimethyl benzene. Our plant capacity is 48,050 kg per hour with conversion of cumin hydroperoxide in CSTR is 90%. Heat release from PBR is negative 1.664 power of 16 kJ per hour and in CSTR is negative 3.317 power of 14 kJ per hour, and this indicates per reaction is exothermic reaction. Catalysts involved in our production is copper oxide nanoparticle and sulfuric acid. Rate reaction of CSTR is negative Ra equals to Kca with rate constant value is 0.00064 per second. Number of stage of distillation column we get is 4 stage, and for superpro and symmetry is used to testify and validate the mass balance to produce phenol. By using MATLAB, the program is developed to find mass and energy balance and to compare with the manual calculation. That's all from us. Thank you.